Yeah, in a quantum world, it would make sense to listen to both of us at the same time, or might make sense, but classically it doesn't work that well, I think. Yeah, I saw there's another question in the chat, but maybe there will be another opportunity tomorrow, I guess, after the Qiskit, or in the Qiskit session, where I guess that will be a possibility to come back to this interesting question, which is probably not that easy to answer in a few seconds. Okay, so welcome back to Monte Carlo methods. Comparatively down-to-earth stuff, and which is much easier to implement than quantum algorithms on classical computers. Yeah, I'm supposed to talk about. I will probably stop in at 3 or a little bit after 3, so I want to keep to the schedule. Probably I will not be able to cover everything that I have prepared, but you can look up in the slides and maybe come back to me if you have any questions concerning the slides. So now I will, based on what we have discussed this morning, I would like to give you a short introduction about Monte Carlo methods and some things one can do with them. And Monte Carlo methods, I use this term a little bit sloppily again. For me, it's just solving problems using random variables. Because in some cases, they are not it's not very well separated from other applications, and so different people who talk about Monte Carlo simulations, Monte Carlo methods, may mean slightly different things, and the field is huge. Not every Monte Carlo person can talk with every other Monte Carlo person, and they understand what each other are doing. And actually, these problems that we solve, they can be based on statistics or rooted in statistics, but not necessarily. The problems may actually have a completely deterministic appearance, such as computing a definite integral or indefinite integral. Sorry, indefinite usually does not make much sense. A definite integral.
Are you supposed to share your screen?
I'm sorry to do that. I made the same mistake again. Sorry. Yeah, actually, the answer is I'm not, but all of you know I was the only one who didn't notice. Okay, you see my screen now? Yeah. Yeah, as I told you, we solve problems using random variables, and the problem may or may not be of a statistical origin. Could be solving an integral, could be solving partial differential equation. Maybe I can talk a little bit on Thursday when I talk about partial differential equations again, because there are also Monte Carlo methods to solve partial differential equations. So let's start with the classical example that many of you may have heard about. So let's assume we don't know the numerical value of pi. We know that pi is the thing that we need for calculating a square. Sorry, the area of a sphere. So pi times r squared, if r is the radius, will be the area enclosed by the circle of radius r. So in particular, if the radius r is 1, then we can interpret this area as the value of pi. And this is the basic idea of this Monte Carlo method to get the numerical value of pi. Yeah? Let's assume we know nothing about pi. It might be 2, might be 100. anyhow, and we will see a much a more complicated example later. And the idea is as follows. Let's assume we can compute the area of a square with a side called a unit square. So it has a length 1 on every side. So it will be consist of the points x, y, where x is between 1 and 0, and y is also between 1 and 0. We all know that the area of this square is 1. And now we want to, we take a quarter of a circle, and let me show you the example. So what we do is the following thing. Here's the code that I need to implement this, and ignore what the estimation of pi is at the moment. So what we do, we know the enclosing the area of this complete square, yep, between 0 and 1 in the x-coordinate and 0 and 1 in the y-coordinate. We know that this has an area of 1. We know that a quarter of a circle with radius 1, yeah, fits into this rectangle, and it has a this area is pi over 4 because it's a quarter of a circle. Yeah, so it's pi over 4, and we are in a scenario now where we know where we don't remember what is the value of pi. We want to compute the value of pi. Yeah, let's assume we should have paid more attention at school. Maybe we remember it's between 2 and 4, but maybe 3, maybe 3.7. We don't know. Yeah, and now the idea of the Monte Carlo method is to throw darts at this rectangle. Assume it's a sheet of paper with an area of 1, and we throw darts and look whether this is inside the circle or outside the circle. Yeah, this is easy to know, because if we add up the squares of the x and y coordinate, if the value is smaller than 1, then it's inside the square. If it's larger than 1, it's outside the square. If it is exactly 1, it will be here on this bluish or turquoise line. Yeah, so it will be on the boundary of the sphere. This is not likely to happen, but it might happen. Yes. Okay, and we do this by sampling random numbers for the x-coordinate, random number for the y-coordinate, and this could give us, for instance, this point here where the pointer is, or the cursor is. Or sorry, let's yeah, assume we have this point. We sum up the squares of the coordinates, and they are a little bit above 1. So we mark this point. We say this is not a hit. This is outside, and we mark as a hit, and the hits are the blue dots. We mark as a hit the points that are inside the sphere or inside the circle. Yeah, that's the idea. And let me move back. Sorry. So something's wrong with my navigation here. Okay. I saw it the other way. So back to these slides here. So here we go. We do the following thing. Here's the algorithm. So we sample n points from a uniform distribution on a unit square. It's a two-dimensional distribution, but it means every component, every coordinate will be a uniformly distributed random number. This is done here. So we sample, let's say we want to throw 1,000 darts at this square. So we take first the x components of the, draw randomly uniformly distributed random numbers, 1,000 pieces, and we assume that each of these random numbers is the x coordinate of one of these points. Then we do the same with the y coordinates, and then we count as a hit when the sum of squares of x and of the x and y coordinates. That's the definition of the circle. If this is less than 1 or equal to 1, then it's inside the unit sphere. Or sorry, unit circle, I should call it in 2 dimensions. And then we count the number of hits. And the probability of a hit, that should be the area of the circle, which is pi over 4, that we know. But we don't know the numerical value of pi, that's the point here. Divided by the area of the square, and this is 1. So pi should be equal to 4 times the number of hits we have inside this, the number of blue points here, divided by the total number of darts that we throw through at the rectangle, at the square, sorry, at the square paper, for instance. So the number of blue points divided by the number of blue and orange points. Every point is either blue or orange. And so this is the total number of points, and the number of hits is when we divide it by that and multiply, divide it by the total number and multiply it by 4, this should be an approximation of pi. And this is implemented here. So basically what we do here, let's just walk through the Python code. Here we have 1,000 data points, 1,000 darts. We compute the x and y coordinates by drawing from a random distribution. You see, it's the total, the distribution is pretty uniform over the whole area. Then we check for every point whether it's a hit or not. Let me just show you what is hit. It's a logical. So we can do this in a second. Oh no, maybe I should do it right now. Because what is hits? I will show you what is hits. It's an array. It's false, false, and so on. You see, these are logical values. Why are these logical values? They say whether the first data point is inside or outside this, the sphere. So it tells me the first data point is outside the sphere. Why is it? Can we see it immediately? Let's let's see x of 0, first data point. And we need to square it. And we have to add the y coordinate of the first data point and decide whether this is larger or smaller than 1. And that's funny. What happened here? This is quite unlikely. Let me test one thing. Okay, something is wrong here. Sorry. Sorry, I know what's wrong. I overwrote x and y. Sorry, I should not have done that. Let me put this straight again. Yes. So, okay. Again, let's keep this in mind. Let me show the hits. Yeah, I have another value. Okay, so it starts with a false. So we don't need this any longer, but yeah, so we know the first sum of squares should be outside the square, so the sorry, outside the circle. So this should be something larger than. Okay, what's going on here? But it's inside. And the reason is I called it hit, yeah. I convert it into you know, a logical. Sorry, hits is used elsewhere, yeah. It's a logical array. So it's true or false, and I translate it to, in order, because I want to do some arithmetics with it, I translate it to numerical array in order to do some analysis with it by multiplying it with 1.0. So 1.0 times true is 1, 1.0 times false is 0. Yeah. So the array says the first one is inside the square. Yeah, so and this is what we should have expected. Yeah, so and we see it's inside. Yeah, and let's look at hit again. So here we see the second is inside, the third is inside, fourth. So 0, 1, 2, 3, 4, 5, 6, 7. Point number 7 should be outside, and point number 8 should be outside. Let's check this for a moment. 7. This is outside the sphere, and 8 should be also outside. Yeah, and it's outside. And I think 9 again was inside the sphere. Yeah, okay. So 9 is one of these blue points. Okay, so hope this is clear. Let me just see. Okay. Yeah. Okay, what else do we do? This you can ignore if you don't. For the moment, this is just for representation. We don't need this for the Monte Carlo implementation. Yeah, we just count the hits. Yeah, what is the number of hits? I have an array which is filled with ones or zeros. And how do I find the number of hits? I just sum the number of hits. Yeah, so I take hit.sum because I have multiplied it with 1.0. Actually, I think I could have avoided that. Let me see if it works. Yes. Yeah, some of the logicals should also be fine. Yeah. So summing up true values, a logical value. Yeah, if it computes the sum, it takes true as a 1 and 0, sorry, false as a 0. Yeah. So the sum of hits is the sum of trues. So this gives us the sum of the number of the blue points. Yeah, hit.sum should be the number of the blue points. And then we divide this by n due to our formula here and multiply this with 4. This gives us an estimate of pi. And I plotted this estimate, pi est, and I also plotted the standard error. What is the error? That's what we have discussed in the tutorial. we need the standard deviation of fit. Yeah, and the standard deviation can be computed with std hit. NP std dot of hit. Yeah, and we have to divide this by NP times square root of n. Yeah. Yeah, yep. Why is this? Because we multiply every point in the sum with by 4 over n. Yeah. So the when we scale this variable hit dot sum by 4 over n, we scale this standard deviation by the same number. I'm sorry. This. Yes, we scale the standard deviation by the same number. Yeah. Okay, so we get the estimate. This is this one, 4 times the number of hits, and then we can take the empirical standard deviation. Yeah, this is just a set of zeros and ones, but they have a standard deviation. No? There's a mean value of it, and we can compute the mean values of these zeros and ones, and then divide this by the square root of n. Yeah, this is the square root of n law that we had just had in this tutorials. Yeah, and we see we get an estimate. We of course we remember from school what is the exact value of pi. We can read it, or we no, it's 3.14159 and so on. And we are, of course, we had only 1,000 shots. Only in the past this would have been a large number, but for a computer nowadays 1,000 is not a large number. So it's about it's not exactly pi, but we get an estimate, and we get an error estimate. Yeah, so this is one standard deviation. If I want to have the 95% error, we would have to multiply this with 1.96. It depends a little bit on your community whether you multiply it with 1.96. Yeah, because this 95% confidence interval. If you are in life sciences, you know that this is usually what would be called statistically significant. And in physics, I think it's a little bit more common to have one standard deviation. Also because the error looks smaller then. Yeah. Okay. I ran it again, and we see then it's 3.015, 3.18. But it's in most cases, in 2/3 of these cases, it should be around the mean plus or minus this standard deviation, which is sigma squared times 4 over n, 4 over square root of n. Yeah, and we see that this works nicely. Yeah? Okay, here we are slightly outside. No, sorry, we are inside the interval, no? Because 3 plus 3.18, the upper limit would be 3.11. Sorry, yeah, 113. No, so, okay, then we are slightly outside the confidence interval. Yeah, but 1/3 of the values will be slightly outside, and if I had multiplied this with 1.96, it's a little bit larger than again. Okay, so that's this first example. Before I proceed, I will have a short look at the chat, but nothing happened there. First example that probably many of you have seen before. Well, and from this example, we can already see some of the nice properties of Monte Carlo methods. So this was not very difficult to implement, and this is typical for Monte Carlo methods. So MC Monte Carlo is often easy to implement. And the idea is that we estimate expectation values from sample means. Yeah, that was what we did here. And we know from the central limit theorem, we have an idea about the error of the sample mean. That's very useful, a very useful property of this Monte Carlo methods. It also comes with an error. Yeah? So okay, I give up with my slide present with a slide variation. I will stick here. I stay here. Yeah. So we there are some other methods competing with Monte Carlo methods, but they suffer from all numerical methods are usually approximations. You don't you rarely get the exact number from a numerical computation. And it's very valuable when the numerical computation comes with an idea of the error. Yeah, for instance, when I know that from a Monte Carlo method, my Monte Carlo method gave me this result that I have here, 3.108, and then I know the this standard error of about 0.05. Yeah. Okay, so this standard error of 0.05. You know, the Gaussian distribution ranges from -infinity to +infinity, but most of the things take place around the mean ± 1 standard deviation. Yeah. So 68%. With a 68% probability, your real value of pi will be in this interval. If you double this interval, you say, okay, I'm not so sure. I want to have 95% confidence interval. So you multiply this by 1.96, which gives you about 0.1. Yeah, so you say you find out, okay, my real value of pi might be 0.1. But it might also be 0.0, so exactly 0, or it might be 0.2, but it's not very likely that it's 2 or 4, yeah, because that would be many standard deviations away. Yeah, so what does this tell us? This tells us basically, you see, plus minus 0.05. This means basically we know that the first digit is probably correct. Yeah, and we have discussed what do we have to do if we want to have the first 2 digits. Yeah, yeah, then we have to multiply this by first 2 digits means we need an accuracy which is larger by a factor of 10. Yeah, so larger by a factor of 10 means we have to square this. Yeah, so we have to have 100,000 data points. Now you see this looks a bit better, and you see the first 2 digits. Yeah, you see this is just rounding 0.05. The first 2 digits are approximately. So if I have 0.05, it means that still, you know, rounding. That it could be 0.1. It will be between 0.14, sorry, 0.13 and 0.16 probably. Yeah. And yeah. Let's see, I make 400,000, then it should be improved. The error should be improved by a factor of 2, so it should be 0.02. So probably then I would get the 0.14 with a pretty high probability. Yeah, and you see it worked. Huh? So this is a very useful thing that we can estimate the error. Not every numerical method comes with this powerful add-on. So let's stop for a second and think what we have learned so far. So Monte Carlo is pretty easy to implement. You don't know much, don't have to know much about pi, other than that it's the surface of the unit circle. Yeah? So, and the basic idea, we sample, we estimate expectation value from sample means, and get an idea about the error that we make. Now let's look for a competitor. Let's do the same thing again. This is not the only Monte Carlo method we can use to estimate pi. Now we have to add a little bit of knowledge about calculus. Let's assume we formulate it as an integral. Now we know that, let me show it to you here in this figure. When we know that the surface will be 4 times this gray area, so this is the area under this a quarter of the circle. Yeah, so we take the first quadrant of the integral, first quadrant of the circle, or the intersection with the first quadrant, and we know it will be 5 times the integral under this blue curve. What is the blue curve? It's what we see here. That is defined by all positive x and y that fulfill this equation: x squared plus y squared equals 1. You know, this is the defining property of the defining property of the circle. And now we solve this for y. So we bring x squared to the other side of the equation. Then we know y. This is the function value. If we regard the blue curve as a graph of a function, then the graph of the function will be graph of the function squared. The y value squared is 1 minus x squared. So if I take the square root of it, I get this this law here. Yeah, so it's square root of 1 minus x squared dx. And this is an integral, and an integral that the non-mathematicians may have to struggle with. Yeah, it's not an impossible integral. I could show you how to solve it analytically, but that's not the point here. And we want to save more complicated problems later, where we have no chance to find it by the analytical solution. Yeah, so let's take this definition of pi. 4 times the area under this curve. Hope this is clear, the problem formulation, and we want to solve this with the Monte Carlo method. Okay, and there I'm pretty sure or not so sure. If you're a bit familiar with Monte Carlo methods already, you might have an idea, but otherwise you might not have an idea. Okay, yes, I'll just give a pretty short answer to a question. Can Monte Carlo method be used for inference? Yes, it can. You can use it. In particular, in Bayesian statistics and a lot of machine learning, you use the Monte Carlo methods. And another question is, would the computation of pi work with numbers other than random numbers? Yes, indeed it would. Yeah, you could solve it on a regular grid. I will come to that later. You can do it with other methods. You don't need Monte Carlo methods, and you can also you would get a higher accuracy with quasi-random numbers. Yeah, you know these random numbers that look a bit randomish, but are more evenly distributed. Yeah, so the answer to both questions is yes. But I cannot discuss it, unfortunately. Maybe we can come back to that in the tutorial. Okay, now let's translate this to statistics. This does not look like statistics at all, yeah, and we don't see how to where we can formulate this as a Monte Carlo method, right? Yeah, and the idea is, yeah, we do this. We use the knowledge that we have from our tutorial. we know the density of a uniform distribution is it has a constant density on the interval 0, 1. Yeah? On the interval 0, 1, it is constant equal to 1. Yeah? So let's think here in front of this x, we put a 1. So this will be identical with the uniform distribution. And what do we see here? We see the expectation value of f of x. X is a uniformly randomly distributed number. Then we draw a uniformly distributed random number and then compute the function value of this, and then take the expectation. Yeah, and now, yeah, think again. We want to have the expectation, and sorry, what was my slide? Yeah. And now we estimate the expectation as from the sample means. So what would the Monte Carlo method look like? We draw our samples uniformly distributed, then apply this function x, f. This will be square root of 1 minus x squared, and then take the average, take the mean, and that's all. And this will be our Monte Carlo estimator. And now the idea is we don't take the random numbers itself, but we apply a function to it. We apply this function. What is the function? It is this one. Yeah. So we draw a random number, put it into this square root function, square root of 1 minus the random number that we have drawn, and then take the ensemble average of the sample average of it. Yeah. And this is done here. Here's the complete code. Hopefully, I hope a little bit that you are impressed. In particular, if you are afraid of integrals. Yeah? So this looks frightening to many, but we can actually estimate it in a very small number of code lines. Yeah. So. Yeah, idea is we just interpret this as an expectation value of f of x, yeah, where x is drawn from this uniform distribution, and we can imply this immediately. Yeah, so let's start again with 1000. Yeah? Here, forget about seed numbers. So we sample from our uniformly distributed from our uniform distribution between 1 and 0, or 0 and 1. Then we take the square root of 1 minus x times x. Yeah, so that's a nice feature of NumPy. You can apply it vector-wise. Yeah? So this means that every entry in this flat array will be multiplied by itself. Yeah, and this, yeah, and 4 times the mean of this function evaluated on the data. That should be my my Monte Carlo estimate for this integral. So this should be about pi. And again, I can also get an error estimate. Now, so the error estimate will be, again, 4 times the standard deviation of f. You see, so f dot mean, that's the same. I could have already, so it's an alternative to np dot mean f. Yeah? So that's the same. You could either write np dot mean of f or f dot mean without argument. And same with the standard deviation and the variance. This is a shorthand. Maybe in some cases this is more. This is a bit simpler. Yes, so we can also get our error estimate by the fact that we can take this the variance, the square root of the variance divided by the square root of n. And this will be our Monte Carlo error. Yeah, and let me run it. And we get an estimate. No, okay, this one is now we're a little bit outside the confidence interval. But as I told you, 1/3 of the data may be outside. Yeah? So our estimate would be pi is between 0.04 and 0.011 or so. Yeah? So actually it's a little bit higher, but if we run it again, we see another estimate. Yeah? Now it's a little bit too high. But let's, yeah, okay. This is basically this alternative method where we sample from a one-dimensional distribution. So there are often many ways to implement this. We can do it. We had a two-dimensional variant. And let me run this again for 1000 in order to, for the next step. This was for 1000. And just in order to compare it. And yeah, this is for 1000. We get a pretty decent estimate for pi here, but this is an accident that we have 4 digits correct. Yeah, but of course we can correct it. If we have 100,000 data points, then we have a pretty good estimation of the first two. Usually it should be 0.14. I let it run several times, and you see it's always 0.14. Yeah? And for the next, if I, let's say we are in modern ages, 10 million data points, then we should have the first 3 digits correct. Yeah, and it actually works. Yeah? And so on. 1000. Yeah, so you see that even though this looks completely deterministic by just introducing an artificial random variable, we can translate this to a Monte Carlo problem and evaluate this with Monte Carlo methods. Okay. So now the question is, we have 2 methods, a one-dimensional random distribution based on a one-dimensional random distribution, and another one based on a two-dimensional random number distribution. Which one is better? Yeah. So basically what we are doing is we are summing up the height of these green things for the one-dimensional distributions. This is also for this is both for 3 data. 30 data points. Actually, and actually the two-dimensional one is a little bit it's a little bit unfair comparison, because it's even worse for the two-dimensional distribution, where I have to because there I'm using 60 random numbers and I'm only using 30 random numbers for the one-dimensional. So this is already an unfair, maybe an unfair comparison, but keep this in mind that we use more random numbers in the two-dimensional case. And yeah, maybe you get the gut feeling that we have more information that we can use by averaging these values here. So 1 point carries more information here for the 1D distribution. For instance, you see that here we have 2 points with very close 2 x coordinates very close to each other, but they are, one is inside, one is outside. And same here. So maybe you have a gut feeling that the 1D method should be better. And actually one can show that the 1D method should be better. And this is also reflected in the standard errors. Yeah? And we can already see it without doing the analytical calculation, which is possible, but we can also see it from what we when we make an experiment. Yeah, so here with 1,000 two-dimensional points, we get an error estimate of 0.05. For the same number, n equals to 1,000, here, we get an error estimate which is approximately half of it. At the price that we do have to do a little bit of more of a computation, because taking a square root. This is not terribly complicated, but also keep in mind that the one-dimensional method is already better, because it only uses half of the random numbers. Yeah? So when we say n equals to 1,000, it means 1,000 random numbers for the one-dimensional, but it means 2,000 random numbers for the two-dimensional variant. And actually, it will be a little bit better if we say a fair comparison should be the numbers of random numbers that are used. Yeah, so if we make a somewhat fairer comparison with n equal to 2,000, we see that it's even better. Yeah, so it's by a factor of around 2.5, 2.6, 2.8 better. But let's be conservative and take 1 equal to 2,000. So it's important to there's always these the variance or the standard deviation equivalently that you want to have as small as possible. So and one can actually show it that the 1D solution is better. The mathematics is a little bit more involved. You actually have to take the some two-dimensional integrals, and but it's not, it's and the value, actual value of pi enters. That's that would make it a little bit more confusing. So you can show it that 1D is actually better, but in a way, it also contains knowledge about the value of pi, which we wanted to compute in or estimate in the first place. So it doesn't make much sense, but you can show that it actually has a smaller variance and actually has a smaller Monte Carlo error. But we already see it also from we can see it by simulation only, yeah, because the we can estimate the samples as the sample standard deviation or the sample standard variance to estimate this. And these are usually pretty good estimators. We will do a little bit more complicated integral. Yeah, so this looks a little bit more frightening for the non-mathematicians, because we have an infinite integral and a function, a gamma function that is not a standard function everybody knows. But I wanted to discuss a few other things. So why should we use Monte Carlo methods anyway? So we saw the Monte Carlo error is decreasing with 1 over square root of n, which means if you want to get one more digit correct, this means you want to have an error which is smaller by a factor of 10. And to make it smaller by a factor of 10, you have to increase the value of n by 100. So you have to draw 100 times more random numbers, and the simulation time takes much longer. So this sounds bad. No, is this? But is this really terrible? Yeah. Actually, it's a terrible algorithm if you are doing solving 1D dimensional problems. Sometimes you do it because it's so simple to implement, but it's for a numerical mathematician, it might get him upset because you are using a terribly inefficient method. Yeah, so for Monte Carlo is deemed inefficient for one-dimensional problems. Yeah, and they are to do the numerical integration here with a numerical method like this or this integral. There you would use something called the Simpson's rule. And the Simpson's rule has an error which decreases with h squared, which means, let's assume h is the grid size, and the grid size, if we have do the same algorithm like before for the computation of the area under the circle, we subdivide it by n points, then h is 1, the length of the interval divided by n. And we need to evaluate the function at every grid point. Yeah, so this means that the error is of the order of magnitude n squared. And this is much better. So this means if we increase the number of grid points by n, by 100, then the error will be decreased by a factor of 100 squared. So by a factor of 10 to the minus, by a factor of 10 to the minus 4. And only by 10 for Monte Carlo method. Yeah, so this looks really bad for Monte Carlo methods. But there's this thing called the curse of dimensionality. So let's assume you want to have solve an integral in d dimensions. So in 3 dimensions, 4 dimensions, 5 dimensions, or anything else. And we try to do something like Simpson's rule. Yeah, there's a generalization of Simpson's rule for higher dimensional problems. So we divide the hypercube into smaller hypercubes with length h. And then you can come up with an integration method that has error order h squared. Yeah? So this is quite nice, or may appear nice. So what is the number of grid points? Let's assume we have this function is defined on the unit hypercube. So every dimension has size 1. It's going from 0 to 1. And we have a d-dimensional vector, let's say a 300-dimensional vector, and we want to integrate over all dimensions. How many grid points do we have? Yeah, the number of grid points is 1 over h. And we have this in every dimension. So the number of grid points will be 1 over h to the power of d, which means that we need 1 over h to the power of d function evaluations. What will be the error after n function evaluations? This will be after n functional evaluations, that will be of the order h squared. This will be 1 over n to the power of 2 over d. Yep. Okay, and now let's plug in some values of d. As I told you, for one-dimensional problem, if d equals 1, this is of order 1 over n squared. That is what we had for 1 dimension. For 2 dimensions, it would be of the order 1 over n. For 3 dimensions, it would be of the order 1 over 2/3. For 4 dimensions, it would be of the order 1 over n to the power of 2 over 4, which is 1/2. So that means for d equals 4, we have the same order as for the Monte Carlo method. So now what would happen if we have a 100-dimensional problem? Then we have n to the power of 2 over 100. So n to the power of the 50th root of n. And this is ridiculous. Yeah. So for d equal to 100, it would be n to the power of 1 over 50, which means that if you increase the number of function evaluations, corresponding to the number of Monte Carlo random numbers that you draw, if you have increased the number of function evaluations by a factor of 100, this would make your code run 100 times slower. And what would you win by doing this? Yeah, this would reduce the error by a factor of 1 over square root a 50th root of n. So by a factor of 100 to the minus 1 over 50. And most of us are not able to compute this, so let's do Python for it. So the error would be after you have 100 times more function evaluations, it would be 0.9. So you reduce the error by only 10%. Yeah, but it takes 100 times longer. What would be the... So this is not impressive. What would be the result for Monte Carlo methods? There you would have you would reduce by 1 over square root of n, so by a factor of 10. Yeah, so the factor would be the error would be reduced by a factor of 0.1. So you have a 90%, not a 10%, a 90% error reduction with Monte Carlo methods. And now think how many function evaluations you would have in order to reduce the error by a factor of 0.1 with a regular grid, with the Simpson's method. You would have to take, you would have to evaluate it such that the error, this increases with a factor of n to the minus 1 over 50, that this is 0.1. Where does this take place? Yeah, 0.1 is, so the 50th root must be 1 over 10. And this means that t should be 10 to the power of 50. Yeah, and this is a ridiculously large number. So it would be, for a 100-dimensional integral, it would be completely impossible to get the same error reduction as you get for Monte Carlo methods. Yeah, and that's why Monte Carlo methods are actually pretty good for high-dimensional problems. Yeah. So unfortunately, we are now in at the end of my session. Maybe I can come back to a few things, maybe later in the tutorials. I will let you decide. You can write me about your preference in the chat later. I had a demonstration how we can successfully compute the Monte Carlo results for higher dimensional problems. Let's assume we want to have the volume of the unit of a ball in d dimensions. Yeah, you know that the surface is pi times r squared of a two-dimensional ball. So which is a circle. It's 4 pi over 3 times r to the third. Yeah, and for unit sphere, r would be 1. So the volume of the three-dimensional unit ball is 4 pi over 3. And for four-dimensional for the four-dimensional ball, probably most of you don't know the value. Actually, but one can compute it analytically, but we can also estimate it by Monte Carlo method. Yes, so that's what I wanted to show you. Maybe we can do something in the exercises, in the tutorials later. Yeah, so I don't want to deprive you of your break. You have deserved it, I think. So let me have a brief look at the chat. There's one I can discuss later in the tutorial. Come back to that. Okay, yes. Okay, I will do so. Yeah, okay, so let's stop here and proceed at least a little bit. But you have the slides available. Maybe these are also helpful, because I'm sure that we cannot go through all the stuff during the tutorial. Yeah, so have a nice break and see you at 15:30 again.
Thank you very much, Uwe. Thank you very much.